Presented by Caltech.
Ladies and gentlemen, good afternoon. Welcome to the afternoon session of the Science and Society Conference in honor of Ahmed Zewail. This morning was an extremely rich series of presentations on fundamental science. And as rich as it was, I would say it's an appetizer only to this afternoon, where we have even more, including a show and tell presentation by Dr. Phillips, who I'll introduce in a minute. I'm Nathan Gardells, the editor of the World Post. When I was talking to Ahmed at the break, I was complimenting him on his presentation this morning, where he so eloquently intertwined his personal life with his scientific life. And he told me I didn't want to make it too scientific. And then I realized why you asked me to moderate the afternoon session. So I first met Dr. Zewail after 9/11, when I wanted to understand why he was the only Arab to win the Nobel Prize for Science. What was going on that was separating the turmoil in the Middle East from what's going on in the West? And that conversation, as you can imagine, immediately turned to education and the need for knowing, which ultimately is manifest today in the actual, real, concrete acres and students of the Zewail City of Science in Cairo, which was always Ahmed's dream, to create a Caltech for the Middle East. And he does what he says, and he sticks to it. Now, the discussion we had about science and the Arab world continued, I guess you'd say, in the Arab Spring, when the Arab Spring erupted. And at that moment, Ahmed, and people who are not in Egypt don't realize, he is like Yuri Gagarin, the Russian astronaut who's above the fray, a figure that everyone knows. And during that period of turmoil, the pleas were very real for Ahmed to become president of Egypt. He was seen as the conscience of a nation, and he was seen as a unifying, stabilizing figure amid the turmoil. Now, he took David Baltimore's advice, as we heard this morning, and stuck to science and to truth and not to politics. And whether that's a loss, it's not a loss for science, and maybe a loss for Egypt. But in any case, after that period, Egypt has gone through many transitory states. You had the uprising that overthrew Mubarak. Then you had democratic elections that brought in the Muslim Brotherhood. Then you had General Sisi overthrowing the Muslim Brotherhood. And now General Sisi is President Sisi. And so I think that, and there'll be more transitory states coming down the pike, I'm sure. So I think it was you this morning, Ahmed, who quoted Democritus saying, "Matter is always in flux." And that's true also in politics and society. I think it's fair to say that understanding the dynamics of transition, which has been your scientific pursuit, is more complex in society and politics than even in molecular science. Now, when Ahmed wrote his recent book on world affairs, he asked me to write a blurb, or his publisher asked me to write a blurb, and it was very easy to write, and I'll read it. It's a short one, but it says a lot about Ahmed, and it kind of captures, I think, his essence. I said, Ahmed Zewail is a rare individual. His remarkable scope ranges from exploring the minutest interactions of particles to engaging the complexity of global politics and culture to pondering the far reaches of the universe. His rare qualities as a foundational scientist with a strong moral voice recalls other great figures of the past, such as Albert Einstein, whose clarity of mind and deeply humane nobility of spirit the world today so sorely lacks. This very rich book, the title is Reflections on World Affairs, Peace and Politics, shines as a lamp of wisdom in these troubled, even dark times. Now, indeed, this afternoon's session tracks the scope I mentioned in that quote of Dr. Zewail. First, we have a presentation on atomic clocks and particle physics. Then we move on to the complexities of globalization, and finally to interplanetary exploration. Now, our first speaker is Dr. William Phillips. He is presently at the National Institute of Standards and Technology at the University of Maryland. He's a member of the National Academy of Sciences and the Pontifical Academy of Sciences. In a way, he's the planet's timekeeper. His main research, which will be his topic today, is the physics of ultra-cold atomic gases and how they are used to register precise time, the coolest thing in the universe, as he puts it. He shared the Nobel Prize in 1997 for development of methods to cool and trap atoms with laser light. So, Dr. Phillips, please take the stage.
Thank you. Well, thank you very much. It's a great pleasure to be here. Can we go to my laptop now? This morning, a number of people quite correctly remarked on how wonderful all the presentations were and how scientifically insightful. Now we're in for something completely different. So I'm going to talk about time, Einstein, and the coolest stuff in the universe. And I want to begin by acknowledging the members of the Laser Cooling and Trapping Group at NIST, the National Institute of Standards and Technology, whom I work with every day, Gretchen Campbell, Paulette Trey Porto, and Ian Spielman, and the agencies that have supported this work over a very long period of time. But we're really here to recognize Ahmed Zewail, and I'm particularly taken by the title of his book, A Voyage Through Time, because it seems like time keeps coming up again and again whenever you talk about something. And I love this title because it evokes not just the time of one's life, but also the femtosecond time scale on which the wonderful things that Ahmed is so known for have and are playing out. And of course, we're wishing Ahmed happy birthday. And what incredible timing to be able to arrange for a symposium like this on your actual birthday. Because most people's birthday symposiums are months away from the actual time. So this tells something about Ahmed's time. But you know, one of the things about birthday parties is you want to have fun, right? And I'm not sure how many birthday parties you've been to for 8-year-olds, but one of the common things is that there'll be some sort of entertainment, you know, in the form of a magician or a clown. Now, we already heard this morning that Ahmed was a magician, you know, with Caltech being Hogwarts. So guess who the clown is? So, okay. Time, Einstein, and the coolest stuff in the universe. So what does time have to do with Einstein? Well, Time put Einstein on the cover of their magazine as the person of the century. Not a bad choice. I mean, he did all kinds of wonderful things that really have changed the way that we think about the world that we live in. From convincing us that there really are atoms and molecules making up matter, to the basis of lasers, to one of the fundamental ideas of quantum mechanics and wave-particle duality. But probably the thing that Einstein's most known for is special relativity, that changed our very conception of what time and space mean. And he came to his amazing conclusions about time and space by asking himself a question that I suppose people have asked themselves since the beginning of at least human time, and that is, what is time? What is this thing that is always in the present but will soon become the past? And Einstein answered this question in a way that you might find a little superficial, but in fact is quite deep, that time is what a clock measures. And by taking that idea seriously, he came up with his ideas of relativity of time. But if time is what a clock measures, then you might ask yourself, well, what is a clock? And a clock is something that ticks, something that gives you a periodic set of events. And there's lots of different kinds of clocks. The earliest clock is the rotating Earth. Now, ancient people didn't know the Earth was rotating, but they saw the sun rise and set, and they ticked off days. Later, people found out that a pendulum was a pretty good ticker for a clock and made things like this beautiful tall clock. Some of you may be wearing an antique quartz wristwatch. And inside that quartz wristwatch is a vibrating tuning fork-like structure that's the ticker for that. Now, these clocks, some of them are beautiful works of engineering, some are beautiful works of art, some of them are historic, some of them are quite humorous. This prank at Caltech from several generations ago plays on one of the common ideas about time. But there are many different kinds of clocks. All of these clocks are imperfect in one way or another. Even the rotation of the Earth is slowed by the tides and changed by ocean currents. The quartz watch, every one is made a little bit differently, and it may keep different time depending upon whether you wear it or keep it on the bedside stand. The best tickers are atoms. So why are atoms the best tickers, and what makes them tick? Well, there are differences in energy levels between atoms that correspond to frequencies, and those frequencies can become the ticking frequency for an atomic clock. But one of the things that is so marvelous about atoms is that while every quartz watch is a little different from every other one, every cesium-133 atom, the atom we use to define what we mean by 1 second, every atom is absolutely identical to every other atom in the entire universe as far as we know. So that means that anybody who can get their hands on some cesium can make an atomic clock that will keep the same time as everyone else. And they're very little affected by the environment, so they just make great clocks. Now you might ask, how good are these clocks? Well, and how much do they cost? Well, for less than $100, you can get a clock like this quartz watch that I've been wearing that is good to a part in a million for less than $100, 30 seconds in a year. But for $100,000, you can buy an atomic clock that's good to a part in a million. Now you may say, who's going to pay $100,000 for a clock? But think about this. You pay 1,000 times more money and you get 1,000,000 times better performance. How often does that happen? But you still may ask, why does anybody need a clock that is that good? I mean, after all, we don't really need to know what time it is to that level of precision in order to go about our daily lives. Or so you may think. I would like to convince you otherwise. I found this advertisement in a magazine once. It says, if you buy our high-end car and you get into trouble, relax because help is only 10,000 miles away. And the 10,000 miles refers to the orbiting altitude of a constellation of satellites that make up the global positioning system, the satellite navigation system. And at the heart of that satellite navigation system, the GPS system, are atomic clocks. Every one of those satellites, and there are about 24 of them, every one of those satellites has on board several atomic clocks, and they're all synchronized. So here is a cartoon of that system. So here are a couple of GPS clocks. Here you are with your GPS receiver, and let's imagine for a moment that you also have one of these high-quality clocks in your receiver. You don't, but imagine that you do. All of these clocks are synchronized, so they're all keeping the same time. So at some instant, they all synchronize to one. But they're broadcasting information about what time it is and about what the location of the satellites is. Now, it takes a certain amount of time. You notice how time keeps coming up? For the signal about what time it is to get to you at your receiver. And so when you receive that signal saying that this clock says it's 1, you know that it's really 4, and now you know how far away the clock is because you know how fast the signal traveled, and you also know where that clock is, so that means you're somewhere along here. Well, that's not the only satellite you have, so you've got more than one satellite. And because you have more than one satellite, in a sense, using those multiple satellites, you can triangulate where you are. So knowing the information about where more than one satellite is allows you to pinpoint your location to the intersection of these curves. Now, if you lived in a two-dimensional world, like the screen here, that would be all you would need if you also had a clock. But you don't have a clock, you don't live in a two-dimensional world, so in fact you need 4 satellites. So when you turn on your GPS system and it says searching for satellites, it's trying to find 4. Once it's got 4, it's ready to go, and it can tell you where you are, anywhere on the face of the Earth, to within a few meters. And everybody uses these things. And you can even use it to study continental drift. It's that accurate if you wait for a long time. Now, here's where a really important comment about science and society comes in. General relativity, it's been in the news big time lately because of the wonderful gravity waves, which of course Caltech has had a huge role to play because Kip Thorne and Ron Drever, along with Ray Weiss at MIT, dreamed up this idea of LIGO some decades ago. But general relativity isn't just about gravity waves. If we didn't understand general relativity and the way in which gravity affects the operation of clocks, the GPS system wouldn't work. When general relativity first came out, it was said in the newspapers that only 3 people in the world understood the theory. A theory that was once that arcane now underpins a multi-billion-dollar industry, and the existence of GPS has changed our daily lives. At least it's changed mine. I don't get lost nearly as much as I used to. The message we've been hearing again and again from people today has been, we've got to do basic research. We have to do research that isn't directed towards solving a particular problem. Einstein wasn't trying to solve the problem of navigation. It was the furthest thing from his mind. He wanted to understand what is this thing called gravity. But without that, we wouldn't have the global positioning system. But we might ask ourselves, what do these atomic clocks look like? Well, let's look inside these things and ask ourselves what goes on inside an atomic clock. So here is the oversimplified version of an atomic clock. You've got some cesium atoms, and we're interested in 2 different states of the cesium atom that have to do with the relative position of the spin of the nucleus and the electron. And we start off with the cesium atoms all in one state, with, say, the electron spinning one way, and then you put in microwaves, and this is the ideal frequency. This is what we define to be the frequency separation between those 2 states. And when the microwaves have just the right frequency, it'll make the electron flip. And if it doesn't have just the right frequency, then it won't. And so you tweak up your microwaves until it's just at the right frequency, and now you've got a clock that is ticking at the perfect ticking rate set by the cesium atom. Now that's the oversimplified version. Here's just the simplified version. So you have a beam, you have an oven full of cesium metal, you heat it up to make a gas because you want these cesium atoms to be floating freely in space so you get their natural ticking frequency. And you select them all so they're, say, spin down. You have an atomic beam that could be maybe a meter long in the laboratory. You shine in microwaves, and when you make the frequency, hit the frequency just right, then you know that you're on the resonant frequency of the cesium atoms. Now this is wonderful, and these clocks are amazing. They keep time to better than a part in 100 million, a part in 10 to the 14. But they are limited in how well they can do by a number of things. Einstein's relativistic time dilation, the fact that moving clocks run slow. These things are moving at over 100 meters per second. Doppler shifts, just the fact that something is moving, you will hear its whistle, whether that's sound or light or water waves, you will see the frequency be different depending upon whether you're moving toward it or away from it. This is the way that we know the universe is expanding. This is the way the cops find out how fast your car is going. And it works for the atoms as well. And just the fact that we have a limited observation time, the fact that these atoms are screaming along at nearly the speed of sound, makes it difficult to measure them because they just don't hang around for a long time. So these effects of atomic motion limit our ability to get more out of them to about a part in 10 to the 14. But we want to do better, and at the National Institute of Standards and Technology, it is our duty to do better. And in order to do better, what we're going to have to do is to make the atoms move more slowly. And making the atoms move more slowly means cooling them down, because the difference between hot and cold is the difference between fast and slow. In fact, temperature is simply a measure of the kinetic energy of motion of the atoms or molecules that make up whatever we're measuring the temperature of. So that means that, that the temperature is just proportional to the square of the velocity of these atoms. So what we need to do in order to make better clocks is to cool the atoms down. And so, in order to give you an impression of just how cold we want those atoms to be, I have brought along, courtesy of the good folks here at Caltech, some really, really cold stuff. In here, we have liquid nitrogen. Now, nitrogen is the main component of the air, and that means that this is basically liquid air. It is so cold that compared to it, the floor on which I'm standing is like a red-hot stove. Imagine what would happen if you poured cold water out onto a red-hot stove. It would boil, and that's what's happening here. When I pour this out, it boils immediately because the floor is so hot compared to the liquid nitrogen. Now, given that, and unless you've been in a low-temperature physics laboratory, this is probably the coldest stuff you've ever seen. So if you've got something that cold, then why not use it to cool down your gas so you can slow down the atoms and molecules and measure them better? So here we have a traditional container for hot gas. I'm from Washington, D.C. We refer to hot air. And what we're going to do now is to stuff it into this bait bucket that is full of liquid nitrogen to cool down the gas to make the atoms and molecules move more slowly. So that's what we're going to do. Ooh, that's really satisfying. So what you're hearing is the cracking of the plastic tabletop, because the coefficient of thermal expansion of plastic is so much bigger than it is of everything else, that when you cool a certain portion of it, it makes the interface between the crack, and then that's that loud sound that you hear. And the way I figure it, plastic demonstration tabletop, $29.95. Showing how exciting science is, priceless. So, here is what we call a Dewar flask. It's basically a thermos bottle. It's been sitting out all day at room temperature. Compared to the liquid nitrogen, this thing is red hot. Imagine that you took a metal bucket and filled and put it in a fire until it was red hot, and then took it out and poured cold water into it. Unfortunately, I'm running out. So, but fortunately, I've got more. So, let's fill this thing up. It would boil, and that's what's happening here. This liquid nitrogen is boiling over when it hits the hot Dewar. So we're going to let that boil away, cooling down the inside of the container, and while it's doing that, we're going to cool down some more gas, because we want to make the atoms and molecules move more slowly. The whole idea here is to take a gas where the atoms are free to move around and not stuck to one another as they might be in a liquid or a solid, and cool them down so that they are going to move more slowly. And this is going to happen, to anything that you cool down. It's going to make the atoms and molecules that make it up slow down. I mean, if we were to be able to cool the air in this room, which seems like a good idea, then it would make the atoms and molecules move more slowly. So let's see what else I can do to show you just how wonderfully cold this stuff is. So here is a nice bouncy racquetball, okay? Let's put it in here and see what happens. Now, just to give you an impression of what might go on here, here's a nice stretchy rubber band. Now I'm going to take this rubber band and I'm going to dunk it into this container of liquid nitrogen. I wish you could see what's going on, but it's boiling. I don't know if you can see that through the transparent walls. But the boiling soon subsides because the rubber band is now down to the temperature of the liquid nitrogen. When I take it out, I can break it like it was a dry twig. This stuff is really, really cold. But you know, all I have to do is to warm it up a little bit in my hands, and now it's a nice stretchy rubber band. This stuff is really, really cold. And you know, if you've got something that cold, then why not use it to slow down your atoms and molecules and make them move more slowly? Because if they're moving more slowly, then we can measure them better. We'll have more time to measure them, and they'll be less affected by things like Doppler shifts and other kinds of time dilation shifts and all that. Everything will be better if the atoms are slowed down. Now let's see what else we can do. Okay, now I'm sure that when you were young and were learning to do things in the kitchen, that your parents told you that you should never, ever, ever put a closed container of liquid into the oven. Well, here we have a container, and here we have some liquid. And now, I'm going to close this container up. Nice and tight.
Bill, can you do this away from me?
You'll be fine. And now, compared to this liquid, the room in which we are sitting is an oven. So let's see what happens. Okay, now let's come back to here. Let's come back to here. The boiling in this Dewar has subsided, and I need to top it up a little bit because a lot of liquid nitrogen has boiled away. So let me top it up like that. Now, let's take a nice fresh flour. Okay, this flour been sitting out all day at room temperature. Imagine that you took something like a fireplace poker and heated it up until it was red hot, and then pulled it out of the fire, and then plunged it into a bucket of cold water. What would happen? It would make the water boil. And that's what's going on here. Okay, so the water, the liquid nitrogen is boiling away, and while it's boiling away, let's go ahead and what? Let's go ahead and cool down some more gas, because of course we want to make the atoms and molecules in the gas move more slowly. Having a hard time making my fingers work here to get this tied off. So we don't want any gas to get out. So we'll just cool down a little bit more stuff. Yeah, seems like I'm losing a little liquid nitrogen because so much of it is spilling out. Maybe I blew this one up just a little bit too big, I'm not sure. Anyway, let's refill a little bit. There we go. Okay, that's great. Now, let's see. Let's see what happened to our racquetball. So you remember how nice and bouncy the racquetball was. Now, let's see what it does. It breaks like it was made out of porcelain. This stuff is really, really cold. And, you know, if you've got something that cold, then it seems perfectly reasonable that you should use it to cool down your atoms and molecules, because if they're moving more slowly, it'll be easier to measure them, and in particular, we'll be able to measure their ticking better, and that will allow us to make a better clock. Now, as I've said, this stuff is really, really cold, and unless you've been in a low-temperature physics laboratory, this is probably the coldest stuff that you've ever seen. How cold is it? Well, in order to understand how cold it is, we have to think about the way physicists and chemists like to measure temperature. You know, around here, it probably never gets even below 0 Celsius, let alone below 0 Fahrenheit. But where I come from, it's often below 0 Celsius and sometimes even below 0 Fahrenheit. And we just don't like those negative temperatures. They're nasty, difficult to deal with. And so we've invented a temperature scale where the lowest possible temperature is what we call 0. Now, why is there a lowest possible temperature? Well, remember, temperature is about motion. And something that was taught to us by Democritus over 2 millennia ago, temperature is about motion. And the slower something is, the colder the temperature. What is the slowest something can go? Stopped. So that means if we can stop the motion, then we're at the lowest possible temperature, and we call that absolute 0. Now, it turns out, because of little details having to do with the uncertainty principle in quantum mechanics, even at absolute 0, the motion doesn't really stop. But let's say just between friends, that absolute 0 is where the motion stops. Measured up from absolute 0 in degrees whose size is the same size as Celsius degrees, room temperature is about 300 degrees. Okay? Ice melts at about 273. Dry ice has a temperature of about 195. The coldest air temperature that was ever measured anywhere on the face of the Earth, someplace in Antarctica in the winter at a research station, was 185 degrees above absolute 0. 185 degrees above absolute 0. My friends, this stuff, which is so cold that it boils when you pour it out on the floor, this stuff is 77 degrees above absolute 0. 77 degrees above absolute 0. This stuff is really, really cold. And, you know, that was the whole idea, having something that cold to cool down our gas. And that's why we were putting the balloons in here. But I think that some of you may have noticed that there was a little issue here, that the volume of the balloons that I put in was in fact considerably larger than the volume of this bucket. And the reason for that is that these balloons are as flat as pancakes. They have turned into Frisbees. They are, does anybody know how many of these balloons I put in here? And they were all orange, right? How many brown balloons did I put in? What about blue ones? How about, whoa! Oh, fantastic! Your mother was right. Don't ever put a closed container of liquid into an oven. So what happened was that you can see that the air did not go out of these balloons. You see, there's a whole bunch more balloons in here. The air did not go out of these balloons. What happened was, let's go back to the laptop now. So what happened was that, and this will happen to anything where you make if you try to cool down a gas by cooling down the container that it's in, which is what we did with the balloons, what will happen is if it's cold enough, the gas will condense or it'll stick to the sides of the container and you won't have a gas anymore. And if you don't have a gas anymore, then you won't have this perfect ticking frequency that we expect from our isolated atoms. So here we're faced with a problem. How are we going to cool something down without touching it, without putting it in contact with something else that is cold? And it goes beyond that. This temperature is 77 degrees. It's about 4 times colder, about 1/4 the temperature of room temperature, which means that the velocity of the nitrogen molecules, when I pour this stuff out onto the ground, what's boiling off of here is nitrogen molecules moving about half as fast as they are in the air. In the air, they're moving at about 300 meters per second, about the speed of sound, no accident. And when they boil off here, it's about 150 meters per second, half as fast as the room temperature nitrogen molecules, half as fast. Well, not bad, but I have not spent the last 30 plus years of my life trying to make half-fast atoms. What I wanted to do was to make things that were really, really slow. And so how are we going to do that, and how are we going to do it without touching the atoms? And the answer has been staring at us from the heavens literally for centuries, because since the time of Kepler, people have understood that the tails of comets always point away from the sun. So when a comet comes in from out in the Oort cloud and the dust and gas gets heated up by the sunlight pushes the tail out away and the tail streams behind. And as the comet comes around and goes back out, the tail streams in front of the comet. And it's because, Kepler guessed, it's because of the pressure of the sunlight. And he was right. There's also a solar wind that he didn't know about. But what we're going to do is to use that idea of the pressure of light to cool down a gas of atoms. And in order to understand how that works, I need to remind you of a couple of things. One is that the light will only be absorbed by the atoms if the color, which is to say the frequency of the light, is just right. And it has to be really just right. Optical frequencies, almost 10 to the 15 cycles per second. The range over which an atom will absorb light, typically on the order of 10 million cycles per second, 10 to the 7. So that means you've got to be right to a part in 10 to the 8th, a part in 100 million. You can never tell the difference between two colors that are that close together, but the atom can easily tell the difference because it is so sensitive to the color. You have to be on resonance in order for the atom to absorb the light. The other thing is the Doppler shift. We already talked about that. If you're moving toward a source of light, it will look as if the frequency is higher. If you're moving away, it will look like the frequency is lower. Now we know enough to understand how laser cooling works. This idea in 1975, Wineland and Demelt, Hensch and Shallow, all four of those people have won Nobel Prizes for something else. So imagine that I am this atom, and I'm moving to the left, and we've got a laser beam, and the frequency of the laser beam is a little bit too low for the atoms to absorb the light. But this atom moving toward this laser beam sees it Doppler shifted up in frequency. That makes it look like it's the right frequency to absorb. It absorbs it and slows down. Whereas this atom, moving this way, thinks that the frequency is even lower, and it was already too low, and so it won't absorb it much. But of course, if it did, it would speed up, but it doesn't do that much, so this is looking good. And all we have to do is add another laser beam from the other direction, and now this atom will pick out this laser beam to absorb, while this one picks out this laser beam. And now we can bring in laser beams from all directions, from top and bottom and backward and forward, and no matter which way the atom is going, it feels a force that opposes its motion. It feels as if it is in a viscous fluid. Remember, Jeff Kimball told you about optical molasses in this wonderful video from his postdoc. That's what this is. The atom feels as if it's in a viscous fluid because no matter which way it's going, there is a force that opposes its motion. And you can then calculate using ideas that Einstein taught us in 1905 about the photon nature of light and the way in which this is going to cause the motion of the atoms to become randomized and heated up. And you can calculate what the temperature is. And you calculate that the lowest possible temperature for sodium atoms, which is the first atom that we did this on, the lowest possible temperature was 240 millionths of a degree above absolute zero. 241 millionths of a degree above absolute zero. I want to remind you, this is probably the coldest stuff you've ever seen. It boils when you pour it out on the ground, but it's gone. But fortunately, I've got more. And this stuff is 77 degrees above absolute zero. We're talking about this being 300,000 times hotter than the temperature that we expect the sodium atoms to get to. So people got really interested. Steve Chu at Bell Labs got interested. We got interested. Here's a picture from our laboratory that shows laser beams impinging on sodium atoms. There's about a centimeter across, 100 million atoms. How cold is that gas? How do you measure the temperature of something that is that cold? And the answer is that you measure how fast the atoms are going. So by measuring how fast the atoms are going, we can measure what that temperature is. And Back in 1985, when Steve Chu first did this, he found out that the temperature was 240 microkelvin, exactly what the theory predicted as being the lowest possible temperature. And we measured it a little bit later and got the same thing using exactly the same method. But when we looked into it a little bit more carefully, what we found was that, in fact, the temperatures were much, much lower than what the theory had predicted was possible. Obviously, this is a violation of Murphy's Law. I mean, we wanted to get as cold as we could, and we had apparently gotten colder than we could. We felt an awful lot, well, there was a big discussion about why the temperature was so cold, and out of that discussion, eventually a new theory emerged. And Jean Dalibard and Claude Cohen-Tanucci in Paris, and Steve Chu and his colleagues at Stanford figured out the theory behind it, and then guided by that new theory, over the next few years, we were able to get cesium atoms down to a temperature of 700 nanokelvin. 700 nanokelvin, 700 1/billionth of a degree above absolute zero. Remember, this stuff is the coldest stuff you've ever seen, and it is 77 degrees above absolute zero. We're talking about something that is 100 million times colder than liquid nitrogen. The coldest natural temperature in the universe is the blackbody radiation that fills the universe left over from the Big Bang. It's got a temperature of a little bit lower than 3 degrees. We are 4 million times colder than the temperature of outer space. So when I say the coolest stuff in the universe, I mean it. These atoms are amazingly cold, but as you'll see, that's just a start. How fast are these atoms going? The thermal velocity of cesium atoms at 700 nanokelvin is less than 1 centimeter per second. Now, I want to remind you of the old style of atomic clocks. You have the atoms going along here, a little less than 200 meters per second. You've got a meter-long apparatus, and you have some milliseconds, some thousandths of a second to measure the atoms. Now, what happens if instead you put in atoms that are not moving at 200 meters per second, but atoms that are only moving at 1 centimeter per second into such a clock? What kind of a clock can you make? And the answer is no clock at all, because they drop like stones. I mean, if you've got something moving at a centimeter per second, you let go of it, it's going practically straight down. So this is worthless. Fortunately, many, many years ago, a guy named Gerald Zacharias at MIT said, what if instead of having the atomic beam go horizontally, what if you had some really slow atoms and you made the atomic beam go vertically? You see, if you throw something up a meter, it comes back down after a second. Now, sadly, Zacharias didn't have any slow atoms, so he couldn't make this work. Remember Ray Weiss, one of the originators of LIGO, along with Kip Thorne and Ron Drever? Ray was the student who tried to do that experiment that never worked. Back in the 1950s with Zacharias. But today it works because we know how to slow down the atoms. So this is Don Meekhoff and Steve Jeffords in our clock laboratories out in Boulder, and they've made this atomic clock where they cool atoms here, toss them up, they come back down after a second, and this clock and clocks like it are the best primary time standards ever made. We call them atomic fountains after those jets of water that go up and come back down again. And these things now have an accuracy of a part in 10 to the 16. That's 1 second in 300 million years. But you know what? That's just a start. Dave Wineland, and you heard about these kinds of things from Jeff, using an optical transition, so no longer a microwave one, but something up in the optical range, has made a clock that is in the parts in 10 to the 18 range, but it's not a primary clock yet. It probably means we need to change the definition of what we mean by a second, because with cesium, it's just, we can do better than cesium. But that's not the end of the story. Jeff told you about Junyi, and he's holding atoms in an optical lattice. And these strontium atoms held in an optical lattice are the best yet, almost a part in 10 to the 18. 2.4 times 10 to the minus 18, that is 1 second in the age of the universe. At the National Institute of Standards and Technology, where all this is going on, an agency of the United States government, this is what we call close enough for government work. Now, one of the things that made all this possible was being able to measure the ticking frequency of lasers at optical frequencies, and that led to a Nobel Prize for Jan Hall and for Ted Hench. Today, these clocks are just leading us into new frontiers of understanding about how to keep time and how to make sense of the whole idea of what time is. But now you may ask yourself, where are you going to store the coldest stuff in the universe? That is, let's say you want to hold on to this stuff for longer than it takes for those atoms to go up and down in an atomic fountain, 1 second. Let's say you want to do something else with it, like the kinds of things that Jeff Kimball was talking about, using it for quantum simulation. You want to hold on to it somehow. You want to have a bottle. Let's imagine that this punch bowl is the bottle we want to hold it in. If this bottle were cold, we've already seen what's going to happen. If this ping pong ball is your atom, it's just going to stick. You won't have a gas anymore. You won't be able to do anything interesting. If this thing is hot, on the other hand, which is what it's going to be because nobody knows how to cool down something like this to the temperature of our atoms. If it's hot, then it means that all of the atoms and molecules that make up this bowl are jiggling around really, really fast at the high frequencies that Ahmed Zewail has studied with his femtosecond techniques, and they will bang into our atoms and heat up our atoms and pop them out of the bowl, and we won't have any cold atoms either. So it doesn't seem that we can use a hot bowl. We can't use a cold bowl. We can't use any bowl at all. We have to use a bowl that has no material substance. Let's go to the document camera. Now, I'm sure when you were young, you all liked to play with magnets. Do you remember the first time you held two magnets in your hand and you could feel that they were pushing each other apart without touching? Isn't that amazing? I'm still amazed by that. And we can use that fact. The fact that we can push one magnet around with another, we can use that fact to trap our atoms without touching them, because our atoms, as it turns out, are like little tiny magnets. Let's go over to the video camera. So this little magnet represents our atoms, and this big magnet down here represents our magnetic bottle. Now, the big magnet is pushing up on the little magnet, so right about here, the magnetic force is canceling out the force of gravity, and if I let go of this thing, it should just float right there. And when I do let go of it, what happens is, it doesn't float, it flips over, and it gets attracted to the big magnet, and that's what always happens when you try to do this. And maybe if you had a bunch of magnets when you were a kid, you tried to make one of those magnets float above the others, and it never worked. And that's why, because it always flips over. But you learn something else playing with toys as a kid, and that is that if you spin a top, it won't flip over. So if we spin, and it turns out our atoms are not just little magnets, they're little spinning magnets. So now we're going to take this spinning magnet and lift it to the place where gravity is canceled out by the magnetic field. And but, you know, any 2-bit magician can levitate a woman and then pass a ring around her, very carefully avoiding the wires that are holding her up. But you've never seen a magician do this. You see, this is the real thing. This thing is really levitated. And thank you. So, that's the toy version. Let's go to the actual thing. So here is a movie of trapped atoms. Here we go. This is a cloud of cesium atoms about 1/1,000,000th of a degree above absolute zero, released into a magnetic trap, and just like our little toy top, it's bouncing around a little bit. Now put some more atoms in. As time goes on, the cesium atoms go away because the vacuum isn't perfect. And all the background gas atoms hit our cold cesium atoms and knock them out of the trap. But over time, our colleagues, learned how to make better and better vacuums and better traps, and using a very old idea, you let the most energetic of the atoms escape, what's left behind is colder. This is called evaporative cooling. And using evaporative cooling, these guys in 1995 were able to achieve one of Einstein's strangest ideas. He said, get a gas of atoms cold enough and dense enough, and a large fraction of the atoms will just stop moving. And they did. And these guys got the 2001 Nobel Prize for that. So now we've come to the end of a kind of an odyssey of searching for lower and lower temperatures. And that's illustrated here on this cartoon of a logarithmic thermometer where each tick mark is a factor of 10. At the top, we have a cold temperature, not the coldest ever, surface of the sun, 6,000 degrees. On that scale, room temperature is just a little bit colder. And in fact, liquid nitrogen is only a little colder than room temperature on this scale. Outer space is just a little bit colder than the surface of the sun. Our first measurements by Steve Chu at Bell Labs in 1985 of optical molasses was colder compared to outer space than outer space is compared to the surface of the sun, and that was just the beginning. Today, we're down to temperatures below 500 picokelvin, and we're hoping that in the near future, we'll take experiments like this into the International Space Station and get down below 1 picokelvin. So what's the future? We already have better clocks. Laser-cooled clocks are keeping time in all of the standards laboratories in the industrial world and guiding the global positioning system. You heard from Jeff Kimball about using cold atoms to make all kinds of wonderful quantum measurements, even this scandalously badly known constant, the Newtonian gravitational constant. Cold chemistry, and here's something where we were inspired by Ahmed Zewail's work. With our atoms being so incredibly slow, they can form bound states that are so weakly bound that the time scales are nanoseconds instead of femtoseconds, and we can do the kinds of things that Ahmed has done at the femtosecond scale, but at the nanosecond scale where ordinary mortals are able to do physics. We're using these incredible clocks to test our fundamental understanding of nature. Do the fundamental constants of nature change? We can do that by studying the behavior of clocks. Quantum information and quantum computers and quantum simulation, all things that Jeff Kimball has told you about, some of the implementations of that have been enabled by cold atoms. And perhaps the most important thing are the things we haven't thought of yet. And maybe some of the young people in this audience will be the ones who think of those wonderful new things. And so if you do, you may be part of a research group where people from all over the world come together to try to explore these questions about the most fundamental features of nature. And so we come to the end, but you know, it's not the end because there's always something new to learn. Thanks very much.